Okay, so good morning, everybody. I hope you can hear me and see the screen. If any one of you can just confirm that.
Yes, sir.
Okay, great. So let's get started. We stopped at this point in the last class. We talked about just with getting introduced to the idea of precipitation, the first process in the hydrologic cycle that we will be looking at in detail. And I've also shared some reading material which explains all of these different definitions and so on. You really don't need to memorize any of these. This is not something that is, uh, that is something that you will be tested on or anything like that. It is just information, and it is good to know what these different words mean and what their definitions are and so on. Okay, but the important one is the last bullet, the Indian monsoon. Now, this I expect you to know. I mean, and you should have known this even before you attending this course, that in India we have two monsoon seasons. The first one is called the southwest monsoon. It lasts from around the beginning of June and ends around the end of September. That's the duration of the southwest monsoon. And then the northeast monsoon, also called the retreating monsoon, is from around the first week of October to the second week of December, or December 15th, broadly speaking. So that's the duration of the retreating monsoon. Now, the word southwest and northeast basically come from direction in which the wind blows, and therefore uh, southwest monsoon. Okay, southwest monsoon refers to the winds blowing from the southwest of the subcontinent, which is it starts from the Kerala coast, and there are different names for these showers. It's called the mango showers. It's a season when the mango starts ripening in South India and so on. So uh, they've had different names, but now more or less we refer to it as the southwest monsoon. And then the northeast, of course, comes in from the kind of the northeast direction, and therefore it's referred to as the northeast monsoon. Obviously, the retreating monsoon is kind of an indication that the monsoon begins with southwest, and then as the monsoon tapers down towards September, there is another 2 months or 1.5 to 2.5 months of rainfall, and so it is called the retreating monsoon. But there's no such, it's not retreating from anything. It's just the way uh, we look at the year, so we think of this one as the retreating monsoon. Okay, anyway, so let's move on now. This is as far as precipitation is concerned, and in the specific context of India, we have this monsoon and the northeast monsoon. Other than this, we do have occasional rainfall here and there in the month of April and May. Those are called summer showers or something like that. January, February, March, by and large, throughout the country, you will see there is hardly any rainfall. That's the general pattern. Okay, here and there you might get a little bit of rain, but generally speaking, January, February, March, hardly any rain throughout the majority of the country. If you're in a hill station, if you're in Shimla or Darjeeling or Ooty or whatever other hill stations, it's a different story. But for the vast majority of India, you just get no rainfall between January to around May or so. At least April, May, you'll get the summer showers, but other than that, you don't get much rainfall. Okay, moving. Now, when it comes to measuring precipitation, we usually express precipitation in terms of depth of water. So, for example, you will say that yesterday the city of Mumbai or Delhi or Hyderabad, whatever, received 2 centimeters of rainfall, right? We never say the city received 10 million liters of rainfall. We don't usually say that. Okay. So although of course you can also measure it in terms of volume, but it's impossible. Nobody has that big a bucket. So we just refer to it in terms of the depth of water, right? So many millimeters of rainfall or so many centimeters of rainfall, and then depending on which part of the country, I mean, which part of the world you are in, maybe if you go to England or you go to US or whatever, some of these Western countries, they may say we received so many inches of rainfall. But even that is going out now. There's almost all the countries in the world have accepted the SI units. So everybody refers to rainfall in terms of millimeters or centimeters. Okay. Now, the device that is used to measure precipitation, the classic device that's used is called the rain gauge. Okay, there are different types of rain gauge, right? There are recording, non-recording types. There are telemetry rain gauges. Telemetry basically means a device which has an inbuilt, let's say, a SIM card, for example, right? So what it will do is that device, after it receives the information, it will transmit that information through the SIM card, transmit the data through the SIM card to a remote location, maybe. So sometimes you can say you can do live monitoring of the rainfall received in different parts of the country or different parts of the district, wherever you, by just sitting at one place, because all those devices are sending the information electronically to a server. So the server keeps getting updated every 15 minutes or every 30 minutes or whatever. So you're getting real-time live data of uh, how much rainfall is happening at different parts of the place. Obviously, you can't be present physically at every location. So therefore, uh, in the modern day, most of the rain gauges or weather stations that are installed come with a this telemetry attached to it, right? So basically, it has the ability to transmit that data to a server through the SIM card and so on. There's also another way of measuring rain gauge, which is through the radar measurement, right? So now the radar measurement, generally, if you look at the previous two types, the recording type or the telemetry type and so on, those ones are point measurements, right? I place the rainfall gauge at a particular location, and my that rainfall gauge is telling me how much rainfall happened at that particular point, right? So for example, in this, let's say I have, let's say I have, let's say this is my city, okay, and I have rainfall gauges installed at multiple locations around the city, okay. So at each point, I have installed a device which is measuring how much rainfall happened at that particular location. So it's a point measurement, right? The radar, on the other hand, measures over an area. Okay, so the radar will give you data in a kind of a like a pixel. Okay, so the radar will give you, let's say, it will divide up this area into multiple pixels, and it will give you how much rainfall happened in each pixel. Right? I think everybody knows what a pixel is, right? So you've all taken pictures where you can see the picture is actually made up of small pixels, which just get information on what is the color there. It's RGB, whatever it is, right? If you go into your images, you will see, you take a picture, it's a picture of a beautiful mountain or whatever it is, but essentially what is being encoded in that is each pixel is carrying information about what is the color in terms of what percentage is red, how much is green, how much is blue. And the more pixels you have, the more resolution you have, right? So your camera, your cell phone camera comes with a 16 megapixel camera or an 8 megapixel or 12 megapixel, whatever, right? So the higher the megapixels, the more the resolution, the clearer the images, right? The lesser the resolution, the less clear the images and so on. So that depends on the number of pixels that are available. So the radar also over an area, and depending on the frequency of the radar and so on and so forth, I don't know the details of that. Depending on the type of radar that you're using, you can get fine pixels or you can get relatively larger pixels and so on and so forth, right? Obviously, the radar measurement is going to give you, unlike the rainfall gauge, which is a point location, point measurement, this is giving you rainfall over an area, okay. But there are limitations. You cannot have radar measuring rainfall over the entire country, for example, right? It's very expensive. If you want radar data, then it's collected, specifically for a small area, which is very important. Then you can actually install the required instrumentation and then collect the data. But it's expensive and it's not so easy to get radar to cover very large areas. It can cover maybe a city or a small district and so on. It can't cover the whole state or the whole country and so on and so forth. It's much more expensive. Okay. Any questions to hear? Any questions at all? No questions. Okay. All right. So now we know how we measure the rainfall using these rain gauges. Now, There is also a network of rainfall gauges, right, which is created to be able to cover a large area and to get representative information about the distribution of rainfall over a certain area. Now, for example, if you during some very heavy rainfall, if you read the newspaper, it will say in the city of Mumbai at Andheri, the amount of rainfall measured was 24 centimeters. At the Santa Cruz airport, it was measured to be 28 centimeters or 20 millimeters, whatever it is, right? So you will get numbers for the different locations within this city of Mumbai, right? So why do we have different rainfall gauges installed at different locations? So that you can capture the variability, because the entire place is not going to get one amount of rainfall. The larger the area, the more variable the rainfall will be, right? And typically you will have rainfall gauges installed at some specific locations. Most likely every airport will have a rainfall gauge, right? Because first of all, for the aeroplane to land, they need to know how much rainfall is happening, cloud cover, this, that, wind velocity, and all of that. So they install a weather station at a airport for multiple reasons. Number one, so that for the functioning of the airport, you need information on the wind speed, the wind velocity, the temperature, the rainfall, and all of that. At the same time, you can also use it to collect hydrological data about how much rainfall is being received at that particular location, right? So the rain gauge network is created, which allows us to understand how rainfall is varying over a certain area. Okay, so now this network density, how dense should this network? There are some guidelines available for this. This is the guideline for India, for example, right? So in a area where you have plains, right, alluvial plains and so on, you are supposed to have one station per around 500 square kilometers of area, right? In regions where the elevation is more than 1000 meters, it is recommended that there should be one rainfall gauge station per 260 to 390 kilometers square, and so on and so forth. And then in hilly areas with very heavy rainfall, you need one station per 130 kilometers square, and so on. So you can see that there's recommendations for what is the ideal network density, so that you can capture the variability of rain. I'm sure everybody understands why in hilly areas you need more stations per square kilometer, whereas in the plains you need less stations per square kilometer. Why is that? Why do you need more stations?
Maybe because water will run off in the hilly areas.
Say that again.
The water will constantly be moving or running off in the hilly areas.
Okay, but so why do you need more rainfall stations for that? I'm agreeing with your answer. Water will run off in hilly areas, no doubt about it. But for that, why do you need more stations? Okay, so you can get an answer for this question just by being on campus. When you get, uh, see, you've been on campus for 2 years now, right? And you must have seen two monsoons on our campus. Your first year, second year, now you're in your third year. So if you observe carefully, you will notice that sometimes when you're on campus, it will be raining near the indoor stadium or near your hostel, but not raining at another part of the campus. Have you observed that? You're standing in one part of the campus, it's raining here, it's not raining somewhere else, or other way around. It's raining there, you can see it, but it will not be raining where you are standing. I'm sure you have experienced this. I have seen this multiple times on our campus. Sometimes, when you're driving, you're like, I started from one place, it was not raining. As I started going somewhere, and then it starts raining, or I can see the rain and I just drive into the rain. So that happens because we happen to be in a kind of a hilly area. In hilly areas, rainfall can vary very rapidly, right? Because the air temperature and the humidity all very quickly, so the rainfall conditions can change very easily. So even within our campus is much smaller than 130 kilometers square. Okay, but we see very rapid variations in. Wait a second, what is our campus area? 500 540 acres or hectares? Acres. That's around 200 hectares. which is 2 kilometers square. Yeah, so our campus is 2 kilometers square. This says one station per 130 kilometers square. Anyway, so you see, whenever there's hilly areas, generally rainfall can vary. Even over a short distance, you will see a lot of variability. So you have to have multiple rainfall stations so that you can capture that variability. The idea is to capture the variability. Otherwise, you don't know, right? So that's the problem with not having enough data. You will just not be able to capture the information more accurately. Okay. All right. So let us say we have all of these things. We are measuring rain using these rainfall gauges. Now we come to a connected question. Okay. So let us. I have, this is my area of interest. Let us say, okay, some area I'm just going to draw. Okay, and I have rainfall gauges installed all over the place. Okay, something like this. I have rainfall gauges installed. Okay. Hmm? I find that one of these gauges for some reason is working for 1 month or 2 months or 1 year, whatever it is. Okay, let us say how many, 4, 5, 6, 7, 8. There are 9 gauges in this. Let us say this gauge, let's call this 1, 2, 3. This is gauge number 6. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So gauges 1, 2, 3, 4, 5 are working fine. 7, 8, 9 are working fine. But gauge number 6, okay, suddenly stopped working for 1 month. Okay, and it's in a very remote area, so reaching that is very difficult. So by the time you find out that it's not working, and then you go and uh, uh, fix it, it takes 1 month, let's say. But now suddenly in my data set, I was planning to collect data for 1 year. Out of that 1 year, only for station 6, for one whole month there is no data available. For all the other stations, I have 12 months of data. For this station 6 alone, I only have 11 months of data. Now I have to estimate the missing data, because, right, if I don't do that, then I have a gap in my data set, because data is very valuable. You need to be able to estimate how much rainfall happened at that particular location, in that particular month where the data is missing. Now, easy way of doing it is to just say I'm going to take the average of the remaining rain gauge stations. That seems reasonable. I will just take the uh, uh, take the average of 1, 2, 3, 4, 5, 7, 8, 9, and say that is the rainfall value for that missing month at gauge number 6. Can I do that? Does that seem like a reasonable idea?
So we can use interpolation.
We can use interpolation. Okay. Uh, Sounds correct, but can you tell us what you mean by we can use interpolation? What exactly do you have in mind?
Like we do have some numerical methods to predict the unknown value,
Okay.
like Simpson's rule.
Simpson's rule. Okay. Okay. But that is like trapezoidal rule and all of that, right? That's what you're talking about.
Yes, sir.
Okay. It's possible, but I say that then it involves, it should be easy to do, right? Okay. There's no
But like
uh,
we are giving more weightage to the points that near to the six and giving less uh,
weightage to the
power,
far
like
away, the ones that are far
important.
away. Yeah. So yeah, so the Simpsons rule, whatever you're talking about, those are one-dimensional, 1D interpolation, right? Here you'll have to do 2D interpolation, right? Because these points are distributed in space. Okay. Anyway, so okay, the idea is that there is no correct answer to this. Let us say, for example, I say that on one particular date, all the students come to class, we are going to measure their heights. Okay, we are going to measure the height of all the students who come to class on a particular day. But for some reason, out of one of them is absent on that day. So we have the remaining 29 students, we have the heights, but for the 30th student, I don't have the data. one thing you can do is, but the government has sent an email saying you have to upload data for every single student. So I just come up with some fake number and put it for that missing student and just upload it to the website, whatever it is. Okay, I'm just giving you an example. Okay, somebody, it's not relevant, but the height of that person, you can only estimate it. It's missing. There is nothing you can do to find the exact height. You can come up with different ways of averaging it and come up with the answer, right? There is no correct answer. One way is to say, out of these 20 are boys and 10 are girls. The missing student was a boy, so let us take the average of only the boys, right? Or the missing student was a girl, then you only take the average of the girls, and then that is one way of estimating the height. I would say that's a reasonable way of doing it. Okay. Or you say, hey, you know what? I definitely know that this person is taller than these students, but he's shorter than that student. So then you know the lower limit and the upper limit, and then you try to find out what the actual height is. The actual height you will never know unless you measure. But you come up with some way, hey, a little bit taller than this, a little bit shorter than that, whatever it is, you'll do all of these things to try to estimate it. So that's exactly what this estimating missing data is also we are trying to do. Okay, there is no correct answer. There are any number of ways in which you can do it. There are two generally accepted ways of doing it. One is to say, I mean, both ways are average only. One way is to just take the average of all the nearby points and just substitute it for that. That's all. Okay. So in this case, you will say you will take 1, 2, 3, 4, 5, 7, 8, 9, take the average of their rainfall values for that particular month and close the deal. Or that is one way of doing it. Somebody else will say, wait a minute, why do you want to do that? Let us observe what is the relationship between only for out of the 12 months, only for 1 month you have missing data. Let us take the average of all the other months and compare the average of 6 to all the other ones, how they are, what is the relationship between them, for other months. And then you will see some pattern and then use that pattern to find out how to fill the missing data. Like what he was saying, do some interpolation. This is a little bit more sophisticated way. Okay. So basically, we can keep talking about different ways of doing it. There is no correct answer. I'm just going to say, if I'll give you two examples of using average. If all values are within 10% of each other, okay, just take the normal average. Sorry, just take the average. The word normal also has a different meaning here. Just say arithmetic mean. Use arithmetic mean. MEAN. If all values are not within, if not within 10% of each other, then you use some kind of a weighting method, right? So you weight it with weighted arithmetic mean. It's still arithmetic mean. We'll just solve one problem and then you'll understand what I'm trying to say. Okay. So let's just, the idea is the same. Either you use the arithmetic mean or you use weighted arithmetic mean. Now you may ask me, how did you come up with this 10% number? Why not 5%? Why not 8%? There's no correct answer. Okay. So don't worry about it. We are going to use the rule of thumb. Let's say 10%. Okay. This problem that will make it very, very easy to understand. Okay. The normal annual rainfall at stations A, B, C, and D in a basin are 80.97, 67.59, blah, 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 and so centimeters respectively. In the year 1985, station was inoperative and stations A, B, and C recorded annual precipitation of 91.11, 72.23, and 79.89 centimeters respectively. Estimate the rainfall at station D in that year. Okay, so look at the numbers. I have normal rainfall for A, B, C, and D. Okay, so there is NA, let's call it NA, NB, NC, and ND. These are the normal rainfalls. Normal rainfall means average over a long period of time. So let's say this is 1985. Suppose I have data from 1950 to 2025. I have the rainfall data for every year. I take the average of all those years for A, B, C, and D. I get this 87, 67, 76, 92, whatever it is. Okay. Then I have the actual precipitation received in the year 1985. So I have PA, PB, PC. I have these numbers. PD is unknown. Okay. So this is the setup of the problem. Now you can see are all numbers within 10% of each other. What is 10% of let's say 91.11? What is 10% of 91.11? 9.1. So you subtract 1 from 91, it's what is that? 82. So the other numbers are 72 and 79. They are not within 10%. So you cannot just take the arithmetic mean, right? So do the weighted arithmetic mean. So the way I'll do it is just observe this and let me know if you agree with what I'm doing. I will do PD divided by ND equal to PA divided by NA plus PB divided by NB plus PC divided by NC, the whole thing divided by 3. This is not a one way of doing it is to say PD equal to PA plus PB plus PC divided by 3. That is normal arithmetic mean. Now the weighted arithmetic mean. Okay, the weights is ND by NA, ND by NB, ND by NC. That's giving us the ratios. And then you multiply that by PA, PB, PC respectively, they divided by 3. That gives you this is one way of doing it. Okay. I'm not saying this is the only way, or this is the correct way, or whatever it is. If you have missing data, somehow you have to try and fill it. This is one way of filling it. Okay, so this is the approach that we can use to fill the missing data. Okay, any questions? Right, so if the numbers were, for example, if it was 1.1, 92.23, 89.89, then all the numbers are more or less close to each other, right? Of course, then the normal rainfall will also be all very close to each other. Then you can just do A plus B plus C divided by 3. Be the full way of handling it. Okay, so this is not a big deal. Okay, it's just a silly game. Okay, there's no correct answer to it, but we kind of try to follow some kind of logical way of doing it. That's all. Okay, now that I have my range, I have to present it in a manner that is understandable to people. So there are, broadly speaking, there are 2 ways of presenting rainfall data. At a particular range, I can present rainfall data in 2 ways. The first one is called the mass curve. Okay, so you see what it says, mass curve of rainfall, in which I have on the x-axis, I have time, and on the y-axis, I have accumulated precipitation, centimeters or millimeters, it could be anything. Okay, so what is this telling us? That, okay, so I have days in the x-axis, right? So I have, how many divisions do I have? 1, 2, 3, 4, 5, 6. 6 divisions in a day. Okay, which means it's a 4-hour interval. So this is 12 midnight, 12 to 4, 4 a.m., 4 a.m. to 8 a.m., 8 a.m. to 12 noon, 12 noon to 4 p.m., 4 p.m. to 8 p.m., 8 p.m. to again midnight, and so on, right? So which means what this is telling me is that until 8 a.m., how much accumulated precipitation? 0. No rainfall was observed in the first 8 hours of the first day. Then rainfall started, and by the end of the first day, how much rainfall was received? You just draw a vertical line from here. So this is around maybe 5 centimeters. So between 8 a.m. and 12 midnight on the first day, around 5 centimeters of rainfall was received. Sorry. And then the rainfall continued, it kept going, and then it became flat at some point. Okay, so this time, wherever this is, okay, I think it's, yeah, around 4 p.m. on the third day. First day, second day, this is the third day. Around 4 p.m. on the third day, rainfall stopped. Okay, and then for 8, 12, for 12 hours, there was no rain because the curve is remaining flat. There's no accumulated precipitation. And then again, the second storm starts on the fourth day at around whatever 4 a.m. or something like that. It starts, it goes on for some time, and then again it becomes flat. So here we are marking the first storm is up to 10 centimeters of rainfall in around 2.5 days, and then the second storm is another 4 centimeters because it goes from 10 to 14 up here. So, and then again it goes flat. So this form of representing the rainfall data is called a mass curve. Okay, why do you call it mass? Because centimeters of rainfall, you can think of, if you multiply it by the area of the whatever region you are looking at, you will get volume of water, and then volume multiplied by density, of course, which is 1000 kg per meter cube, you will get mass of water, right? So it's just a way of thinking about it. It's, for some reason, it's called mass curve. Okay, that's just the way it is. Okay, now another way of representing the same information is to do what is called a graph, HYETO graph. So note this word, Hyeto, HYETO. Now the word Hyet, HYET, is a Greek word which means rainfall. Okay, so this Hyeto graph is a way of representing rainfall that happens. Now this one also has time on the x-axis, but instead of accumulated rainfall, which is centimeters, it has rainfall intensity in centimeters per hour on the y-axis. Okay, so what does it say? It says in the first 8 hours, from time t equal to 0 to time t equal to 8 hours, the rainfall was at an intensity of 0.3 centimeters per hour. For the next 8 hours, it was at, let's say, 0.25 probably. Okay, and then for the next 8 hours, it was at close to 0.4 centimeters per hour, and so on. Right? So these are ways of representing the same information, right? The same information, the amount of rainfall received, I can represent it as a mass curve, or I can represent it as a hyetograph, where the word hyet is a Greek word which means rainfall. Okay, now if you want to think about it mathematically, you take the mass curve, differentiate it, you find the slope at any point, that will give me the hyetograph. You take the and integrate it, you will get the mass curve. Correct? The integral of this is the area will be centimeters per hour into hour. So it will give me centimeters. How many centimeters of rainfall was received from 0 to 8 hours, from 8 to 16 hours, 16 to 24, and so on. Right? So mass curve, you differentiate it, you get the hyetograph. Hyetograph, you integrate it, you get the mass curve. Right? That's it. Fairly straightforward. Nothing very difficult or anything complicated. Any questions before we move on? Yeah, it's a little uncomfortable that there are no questions. There's only me talking. It would be nice if, even just for fun, if you ask me a question, it would be good. Anything to stop the boredom. Okay. Okay. So now we have discussed rainfall gauges. We have discussed how to estimate missing data. We've spoken about how to represent the rainfall data in the form of a mass curve or a hyetograph. Now, I am interested in figuring out what is the mean precipitation over an area, right? Over an area. Because the rainfall gauges represent rainfall values at a particular point, right? At a particular location, this much rainfall was received. Another location 20 kilometers away or 15 kilometers away, I measured another value of rainfall. At some other location, 15 kilometers away, another value of rainfall was recorded, and so on. But when I want to do a hydrological analysis, okay, typically what is expected is that I should know how much rainfall happened over this area, right? I want to know how much rainfall happened over an area, but what I have is point values at different locations, right? So again, I'll go back illustration. I have some area like this. Let's say this is my city, or it could be my district, or it could be my campus, right? Of course, that is relatively small. If you go to a large city, then you'll see variations. Okay, I'm installing so many gauges all over the place and getting point values. At this point, how much rainfall was received. At that point, how much rainfall was received, and so on. But to do an analysis, right, I want to know the average rainfall received over this entire area. What is the mean precipitation over this entire area? What should I, how do I find how much, what is the mean precipitation received over this entire area? So now for this, there are, again, I'm just showing you three doing it. There can be n different number of ways to do this. There is no correct answer. Okay. Whatever we are doing is to come up with a as good an estimate as possible. It might not be the perfect estimate. There is no such thing as a perfect estimate. Okay. But we try to do the best we can. The more data I have, the better my estimate will be. Right. The more data points I have, if instead of 1, 2, 3, 6, if I install more gauges, then I'll get more precise estimate, right? Because I'm capturing more and more variability. But if I keep installing more and more gauges, it becomes very expensive, because every gauge will be 5 lakhs, 6 lakhs, whatever it is, depending on how sophisticated the equipment are, right? So I might not be in a position to install so many gauges over this area. I'll try to minimize my cost and install only, however, what is the minimum possible number of gauges I can install. That will be the number that I do. But still, I want to find out what is the mean over this entire area. Okay, so I'll just get rid of all this. Okay, so I only have these 6 points or whatever. Okay, so one way of doing it is to just take the arithmetic mean method, which is again the same. Take all the values from all the stations inside that area, take the arithmetic mean. Very simple. A plus B plus C plus D plus E plus F divided by 6. Boom, done. Simplest way of doing it is the arithmetic mean method. I don't think I need to explain anything beyond that. Okay. The next method is called the Thousand polygon method, sometimes also referred to as the Voronoi polygon. Don't worry about the names. The name is not important. The approach is what is important. So the Thousand polygon method is one way of estimating the mean precipitation over an area. It is also an interpolation method. Somebody was talking about we can interpolate. So Thousand polygon method is a simplest interpolation method possible. It's you can think of it as a zeroth order interpolation. It's not even a first order interpolation. It's a zeroth order interpolation. Okay, so just watch. Okay, we'll just solve one problem. I'm not going to describe the procedure. Instead of that, we'll just solve one problem and then you'll understand what to do. Okay. Then the third method is called the iso-Hayatal method. Now, in the previous slide, we saw that hyetograph, where the word Hyet, Hyet is the Greek word for rainfall. So now there's already a clue from this word iso-Hayatal. What would an iso-Hayatal be? What would an iso-Hayatal be? Somebody's got to speak up. Dharvika, are you there? Not there. Okay. Who else is there? Shashikant. Can you guess, Shashikant, can you guess what an iso-Hayatal might mean?
Yes, sir.
Go ahead.
Sir,
It's a guess. If it's wrong, it's okay, no problem.
sir, maybe having same amount of precipitation at some point.
Yeah. So the word iso, when you add that to anything, it becomes a line that joins points which have the same amount of rainfall. right? You must have heard of isobar, which is a line that connects points which have the same pressure. What else? Where else have you heard the word iso? Isosceles triangle, a triangle in which two sides have the same equal length. It's isosceles. So something is equal. That's why we use the word, the prefix iso indicates that it is something is equal. In this case, what is equal? Height is equal. Isohyatal means a line that joins points which have the same amount of rainfall. Okay, so if you solve these problems, you will get to understand what these are. So first, we're going to do one problem with the Thyssen polygon method. It sounds very complicated, the procedure. Don't worry about it. I will never ask anybody to do it by hand. Okay, there are software available to do this, and we'll do a demonstration of that maybe in the next week. So don't worry about it. Let's just take a look at a problem and then try to do it with the isohyatal method. In a catchment area approximated by a circle of diameter 100 kilometers, 4 rainfall gauge stations are situated inside the catchment and 1 station is outside in its neighborhood. Okay. The coordinates of the center of the catchment and of the 5 stations are given below. Also given are the annual precipitation recorded by the 5 stations in 1980. Determine the average annual precipitation by the Thyssen mean method, Thyssen polygon method, Thyssen mean method. Okay. So point 1, 2, 3, 4, 5, the coordinates are 30, 80, 70, 100, whatever coordinates are given. The precipitation received at those 5 locations are 85, 135, 95, whatever centimeters. And the center of the circle, the coordinates are 100, 100. Okay. Now, again, I'm not going to ask you to do this by hand. That's the objective of this. But just to understand it, the first step you do in the Thyssen polygon method is to draw a triangle. Oh, sorry, connecting these different points. Okay, let me try. I'll do one triangle. If I try all of them, I'll just completely mess it up. So maybe I'll do 2, 3, 4. That looks a little bit easier, hopefully. Not bad. Oh my God, I'm on a roll. Oh, messed it up. Yeah, pride goes before a fall. That's what they say. If you feel too proud, then you'll get a kick. Okay, so I've created one triangle. Now then, what you do is in this triangle, you draw perpendicular bisectors. Okay, let's assume that's perpendicular and bisecting. It's neither, but that's okay. And we'll draw one more perpendicular bisector here, and then one more perpendicular bisector here. Okay, now, okay, let me do one more triangle. Then it becomes possible for me to. Okay. So then I'm going to draw another perpendicular bisector here, another perpendicular bisector here. Okay. Okay. Now, take a look at, maybe I'll use a different color now. Just carefully observe. Let's do green. Okay. Oh God. Sorry. I'm trying to draw along the same dotted line. Let me try again. Okay, I hope you all are clapping there. I did an amazing job. Thank you very much. Okay. Sorry. Okay, that's the best I could do. Let's not waste time. Okay. Now, look at any point inside this polygon that I've drawn. Okay, so let's call this A, B, C, D, A, B, C, D, A. If you look at this point, that area we will say is represented by rainfall gauge number 4. Okay, because if you pick any point this area, A, B, C, D, A, if you take that point, any point inside, I pick a point here. or I pick a point here, or I pick a point here, or I pick a point here, whatever it is, wherever I pick the point, which is the nearest gauge for those points, it will be number 4, because it is falling on the other side of the perpendicular bisector. Okay, of course, I've not drawn them all correctly, but assuming that I've done a correct job, then this area ABCDA will represent an area inside which all points have the closest rainfall gauge as number. Similarly, any point here or here or here, the closest gauge will be number 3. Any point here, the closest gauge will be, okay, here I don't know, I've not yet done it, but anyway, the closest gauge will be number 2. And any point here, the closest gauge will be number 5. Why am I doing all this? So that I can divide my total area into areas that represent each rainfall gauge. Okay, I will have, okay, let me try and draw this. Okay, so I have now, what is the area that I'm looking at? My area is this big circle. Now I have divided that area into area 1, area 2, or area 2, area 3, area 4, and area 5. If you add up these areas, what do you get? The total area of the circle, right? And I have found out what is the closest rainfall gauge in each of these areas. So what do? I take the area of the region multiplied by this rainfall received at number 2 plus this area multiplied by the rainfall at this area plus this area into this rainfall plus this area into this rainfall, add them all up, divided by the total area. That will give me the average precipitation received over the entire area. It's a complicated way of finding out the distribution of the areas that constitute this circular watershed. Okay, so just watch this given over here. So the same thing, if you do it properly, this is what you will get. Okay, so you divide up this whole thing into different areas: A, B, C, D, B, C, E, E, C, B, F, and F, B, A. Okay, these are the different areas that this entire thing gets divided into. And because you know the coordinates and all of that, you can find how much is the area. So this area of this ABCD is 2,141 kilometers square. DCE is 1,609, and so on. You find the areas of each of these regions, and then the total area is 7,854 kilometers square. So a fraction of the total area. How do you get that? 2,141 divided by 7,854 is this 0.2726. 1609 divided by 7854 is this 0.2049, and so on. Okay. Now, as it so happens, this station number 1, which is outside, happens to be completely cut out of this analysis. So it's not contributing anything. So although the rainfall is there, it is not contributing anything to this particular area in this particular Thyssen polygon method. Okay. Then you take these rainfall amounts, multiply them by this fraction, and then sum them up. You get the total rainfall. The average precipitation received over the entire area comes out to be 121.8 centimeters. So that's the method. So what have I done? P bar is Pi AI sigma Pi AI divided by sigma AI. That's what I've done. That's exactly what I've done. I've broken up the total area into different areas, A1, A2, A3, A4, so on. And then I multiply that by P1 A1 plus P2 A2 plus P3 A3 plus P4 A4 divided by A1 plus A2 plus A3 plus A4. That's all I've done. Okay, that means the mean precipitation over the entire area. Okay, looks like we are out of time, so I'll stop right now, and we will resume again on Monday. So take care. I will share the notes, and then we will meet again on Monday. Thank you very much. All the best. Thanks, guys. Bye-bye.